In our final discussion in Unit 4, we're going to look at stoichiometry, which is basically looking at quantitative aspects of chemistry. And the first thing that was on our objectives was percent composition. And percent composition is going to be the mass of a component divided by total mass. And so we're either talking about molecules or, in the case of ionic compounds, formula units. And so let's look at these two examples here. Here we have sodium and sulfur, and so combined to make sodium sulfide. So we have 2 sodiums in this compound and 1 sulfur. And so we're going to get this atomic mass from the periodic table for the sodium and for the sulfur. And so we're going to get the total mass of our compound here. And that's going to be 78.046. So for this compound, the percent sodium, and I forgot this is going to be a percent, so we're going to do times 100 up here, but percent sodium is going to be 45.99 divided by my total times 100, and that's going to give me 58.9%. Okay, and then I would do the same thing to get the percent sulfur. And that's going to give me 41.1%. Okay, now let's look. Here's another one, ammonium sulfide. So here I have nitrogen, hydrogen, and sulfur. And remember, this 2 is going to carry through the parentheses. So I have in this compound 2 nitrogens. I have 2 times 4, so I have 8 hydrogens, and I have 1 sulfur. So if we look at the periodic table, we get our masses. Okay, I'll total everything up. Okay, plus. So 68.144 is my total mass, and then we're going to say percent nitrogen then would be all of the nitrogens divided by the total times 100, and so that's going to give me 41.1%. And then I'll let you finish these out or work these and check your answer. So for, let's see, the hydrogen, you should get around 11.8%. And the sulfur, you should get 47.1% on that. Okay, so that's percent composition. Now, let's look at a unit that you are most likely not familiar with. This unit is a unit we use quite a bit, and it's called the mole. This is a counting unit. It's a number that is similar to a dozen. So in other words, in the same way that a dozen means 12, of whatever it is you're talking about. A mole means 6.02 times 10 to the 23rd of whatever you're talking about, whether it's atoms, molecules, anything. Okay, so just to give you an idea, this is a huge number. So just to give you an idea of how big a mole is, here are a couple of things to just kind of compare with. What we want to look at here is the thing to remember about Avogadro's number is that it is a measured value, and even though we primarily use either 6.02 or 6.022 times 10 to the 23rd for its value, you can look online and find what the most precise measuring technique is for Avogadro's number, and you can see how many places beyond what we use that this number is defined. So again, just to emphasize, this is a counting number, and it is 6.02 times 10 to the 23rd of whatever it is that you're talking about. Okay, and we could be talking about, in this case here we have carbon, an element, or water, a molecule, or sodium chloride, a formula unit. But a mole of each of these is the same. Okay, and if we're talking about our ionic substance, if it's 1 to 1, then if we have 1 mole of sodium chloride, that means we have 1 mole of sodium ions and 1 mole of chloride ions. Okay, so let's take a closer look at this. Here's kind of a diagram that is helpful, especially to understand that moles is sort of a connection for us. We really care about the particles, atoms, molecules, ions. The particles are what interact with each other in chemical reactions, and so that's really what we care about. However, these are not so easy to measure, and especially in a regular chemistry lab like ours. And so we need a connection between what we care about and what we're able to measure. And so we can very easily measure mass in grams. And so what the mole does is it is a connection between grams of a substance and the number of particles. So let's see in doing this. So to transition between grams and moles, basically what we're going to do is we're going to use the average atomic masses off of the periodic table. Up to now, we've been dealing with the mass of a single atom or a molecule, small particles, small masses, and so we use atomic mass units. But the neat thing is that the value of a mole is defined so that that average atomic mass, if we express it in grams, the same number, but in grams instead of atomic mass units, then that is the mass of a mole of those particles. Okay, so we can use, in making this transition from grams to moles, we're going to use the values, the average atomic masses from the periodic table. And in transitioning between moles and particles, 6.02 times 10 to the 23rd. Now, the rest of our discussion is going to assume that you have had physics and have had some experience in factor label. I'm going to lay out all these problems in the standard method that you should have learned in physics. If you have not had any experience with this and you need some more instruction, please see me. So let's look at this. How many moles of sodium are in 42 grams of sodium? Well, looking at our little chart here, we can go from moles to grams in one step. That means our factor label is just going to have one step in it. So we're going to lay out 42 grams of sodium. Okay, now what's our conversion factor? Well, we know we need grams on the bottom because we want it to cancel. Grams to moles. And our conversion factor is on the periodic table. It says that 1 mole of sodium is 22.99 grams. So if we take 42, divide by 22.99, we get 1.8 moles. Because our grams cancel, that leaves us with moles of sodium. All right. What is the mass of 0.28 moles of iron? 0.28 moles of iron. Again, we can go moles to grams in one step. We want moles on the bottom and grams of iron on the top. So 1 mole. And if we look at the periodic table, we have 55.8 grams. So 0.28 times 55.8 gives me 15.6, which would round to 16 grams of iron. Okay, how many moles are in 1 times 10 to the 9th atoms? Okay, and we left this generic. Why? Well, remember our grams to moles. In this case, our particle is an atom. Okay, moles to atom. We're not using any specific value on the periodic table. We just use Avogadro's number. So if I have 1.0 times 10 to the 9th atoms, and we're dividing, we want to go atoms to moles. So we're going to divide by Avogadro's number. Okay. So we have there 1.7 times 10 to the minus 15th moles would be in 1 times 10 to the 9th atoms. Okay. How about this? How many atoms are in 7.2 moles of chlorine? 7.2 moles of chlorine. Remember, moles to particles is Avogadro's number. Doesn't matter what type of particle, what element it is. So 1 mole, 6.02 times 10 to the 23rd atoms. And we get 4.3 times 10 to the 24th atoms of chlorine. Okay. Now, here we're going to go from grams all the way to atoms. And if you remember in our diagram, okay, there's 2 steps to go from grams to atoms. So our factor label is going to have 2 steps in it. We start with what we're given. And what I'm going to do is I'm going to lay out my units first. Sometimes that helps if you do your units first and then go back and plug in your numbers. So I know I need grams on the bottom, and I cannot go grams to atoms in one step. I need to go grams to moles first, then I can go moles to atoms. Okay? So grams to moles on the periodic table, it tells me that bromine's mass is 79.9. And then 1 mole is 6.02 times 10 to the 23rd atoms. So 36 divided by 79.9 times 6.02, 10 to the 23rd. And I get 2.7 times 10 to the 23rd. That's atoms of iron. Oh, sorry, bromine. Okay. What is the mass of 1.2 times 10 to the 25th? These are atoms of sulfur. We want a mass in grams. Again, 2 steps. So we're going to go atoms to moles, and then moles to grams. 1 mole, 6.02 times 10 to the 23rd atoms. And 1 mole of sulfur is 32.066 grams of sulfur. So 1.2 times 10 to the 25th divided by, and then times 32.066. So 639 grams of sulfur. Okay, at this point, you might want to pause and go ahead and complete the mole worksheet 1. Okay, that one is focusing just on doing these types of calculations with single atoms. Okay, the rest of our discussion, we're going to look at how do we do the same thing, but when we have molecules or compounds. Okay, and that will be related to mole worksheet 2. Okay, so here we have what is the mass of 0.25 moles of iron 3 oxide. Okay, so let's just lay this out first. All right, if we were going to lay this out, same way as we did before, moles of this, moles to grams is 1 step. Moles to grams. All right, and I use the values off the periodic table. So now we're going to go back to, remember in percent composition, how we found the total mass of the compound. We're going to do the same thing here. So I have, for the iron, I have 2 of those. Oxygen, I have 3. And 9, and iron is 55.85. So I get 1.7. That gives me 159.697, and this is the number, in addition to the atomic mass units, if I'm talking about one formula unit of this compound, this is also, if I have a mole of formula units, this would be the number of grams per mole. So that gives us 39.9 grams of the iron 3 oxide. Okay, so now we're going from number of molecules to grams. So we know we're going to have 2 steps, 52 grams of CO. I want to go grams to moles. Then I'm going to go moles to molecules. All right. Again, carbon and oxygen. 12.011 and 1 oxygen. And so I'm going to add those together. .001. That is my grams in 1 mole. And then 1 mole is 6.02 times 10 to the 23rd molecules. So 52 divided by 28.001 times 6.02, 10 to the 23rd. So that gives me 1.1 times 10 to the 24th molecules of carbon monoxide. Okay, and now let's see. The iron 2 oxide we have 3.01 times, iron 3 oxide, 3.01 times 10 to the 23rd. Formula units. And I want to go from formula units to moles, and then moles to grams. Okay, so the iron, so our compound from before where we calculated that, the grams 159.66 grams in 1 mole, and 1 mole is 6.02 times 10 to the 23rd formula units. And so 3.01 23rd divided by 6.02 10 to the 23rd times 159.66. So we end up with 79.83 grams of the iron 3 oxide. Okay, now let's take kind of a little bit of a step further with this. All right, so say I have N2O5. I have 1.2 times 10 to the 25th N2O5 molecules. All right, and I want to know how many moles of oxygen atoms do I have? Well, the first thing, and this is always, when you're doing these problems, it's always a good first step. If you don't know what else to do, convert it to moles. So let's go from molecules of N2O5 to moles. All right, so 6.02 times 10 to the 23rd. 1.2 10 to the 25th divided by. And so that gives me 19.9 moles of N2O5. Okay, now it wants to know moles of just oxygen atoms. All right, so I want to go from moles of N2O5 to moles of oxygen atoms. Now, looking at the formula, N2O5, that tells me for every 1 mole of my whole thing, for every 1 mole of N2O5 molecules, based on that formula, I'm going to have 5 moles of oxygen atoms. Okay, so 19.9 times 5 gives me 99.5 moles of oxygen atoms. Okay? All right, let's look at another one kind of similar here. Here I have 17.5 grams of ammonium oxalate here, NH4 2C2O4. Now, I need a molar mass for that, so I'm going to just calculate this without writing it out, but you calculate it on your own and see if you get the same thing that I did. Or something close to that. Okay, I got 124.06 grams in 1 mole of my NH4 2C2O4. And now, where do I want to go from there? Well, I don't want moles of the NH4C2O4. I want hydrogen atoms. So not even moles of hydrogen atoms, but hydrogen atoms. So I'm going to calculate the moles of this first. All right, so that's 17.5 divided by 124.06. So that gives me 141 moles of the ammonium oxalate here. And then, all right, so now where do I go? Well, to get from moles of this to moles of the hydrogen, because that's what I'm interested in here. For every 1 mole of the whole thing, how many hydrogen moles do I have? Well, according to that formula, I have 8. Okay, so if I stopped there, I would have moles of hydrogen atom, but the question was asking for hydrogen atoms total. So I have one more step. 1 mole of hydrogen is going to be 6.02 times 10 to the 23rd atoms. Okay, so I have to convert that to atoms. So times 8 times 6.02, 10 to the 23rd, and I get 6.8 times 10 to the 23rd hydrogen atoms.